Good afternoon. So I think we're going to go ahead and get started here. Our next speaker is from Docker, and her name is Ashwini. She's going to be talking about the design of secure APIs for state machines, and we'll get started.
Thank you, everyone. I hope there's no fire in between. So hoping that everything goes well. Today I'll be talking to you about designing secure APIs using state machines. My name is Ashwini. I am a security engineer at Docker. I'm also the author of a pure Python TLS implementation, and I previously worked on Twisted. I really like state machines. I like them so much that I wrote a TLS implementation because I was looking for an opportunity to use state machines in a complex environment. But taking you through an entire TLS implementation is a little too much for a PyCon talk, I think. So instead, we are going to talk about a common problem that web applications need to solve, along with some security implications. We'll then solve the problem using state machines, as promised in the title. So let's dig in. We've all interacted with web applications that ask us to set a username and password. Let's design a service that provides password reset tokens to users who've forgotten their passwords. It should work something like this. The user clicks a button, receives an email that contains a link, which itself contains a password reset token. Clicking the link sends the token back to the service and convinces it that the user should be allowed to type in a new password without entering their old one. Some things to note here. We see that a single token belongs to a single user. If multiple users had the same token, it would clearly indicate a bug, because user A could change user B's password. The one-to-one mapping between token and users has a serious consequence. We should not choose our tokens from an easy-to-guess sequence. If we did, an attacker who got a single token would find other users' tokens and reset their passwords. What we just did here, it's a glimpse of a larger process called threat modeling. My colleagues Ying and David gave an awesome talk on this yesterday, and I highly recommend it. So our first modeled threat is the lack of uniqueness in password reset tokens. And our first API change is to generate long, random tokens via a cryptographically secure random number generator. What this means is that essentially we're taking an enormously long sequence and picking numbers randomly from it with big gaps in between. It's true that if the largest token is very large indeed, nobody would be able to guess anybody else's token in a reasonable amount of time. Maybe then we don't have to worry anymore about our tokens. Maybe we're all done here. Maybe the problem is solved. But hold on, let's take a step back. This diagram also makes it clear that the token passes from one trusted party to another through intermediaries we should not trust. What if the user is using an insecure email server and the token is stolen in transit? Now the attackers don't need to guess the token, it's sitting in plain sight. The threat we initially modeled is no longer relevant. The solution here is to make the token effective only for a certain period of time. That way, if an old token is recovered, it won't do the attacker any good. Since it's randomly chosen, it doesn't tell them about anyone else's token, so after the expiration date, we're back to our original threat. And that's not the end of it. We started out with a simple, common enough goal. But when we actually tried to implement the system, we quickly realized that things can get complicated. And we haven't even looked at any especially convoluted event yet. What if we decide to change the name of the system or migrate all the users to a new system? What if we wanted to reuse the service for a new product, keeping the same users? Implementing the sequence diagram as real code is complicated enough. verifying that the resulting implementation is actually what the design stated is harder. And finally, processes like threat modeling will show us that managing integrity and risk in this process of building the system and maintaining it is impossible without bringing mutable state into the picture. I guess what I'm trying to say here is that global mutable state and shared mutable state are bad, undesirable, but unavoidable at times in the real world. You need to have some state in your program if anything interesting is going to happen. So you're going to have objects. They will change over time. Objects changing over time is a source of complexity. Complexity is where the bugs come from. So what should we do? Is there no hope? Well, let's do some science. Specifically, computer science gives us tools to help manage complexity. There are fields of research that show us how to manage shared mutable state, which is great, and as promised in the title, we'll talk about state machines. If I just go on the internet and try to look up how computer science defines this concept, here's what I get. This is a lot of set theory, and honestly quite dry. There isn't an actionable list of instructions on building a state machine for my web application. I don't know about you all, but I really like pictures. And state diagrams do look quite pretty. So we'll go through this once again in a little bit, getting deeper into the states and what this diagram means. But let's think about all the state user instance might have. Normally, you would have these properties on the user instance. Well, with this design, the state of the user can be in any one of the many combinations of these properties. And by the way, does anyone see the typo in the slide? This happens in real code. We'll need to test the combinations of these properties to figure out what state the user is actually in. And if we add a new property, we don't just have to add one new test. We have an exponential increase in the number of tests we need to write. This makes it hard to maintain, difficult to read, and this is easily buggy. Good luck wrapping your code base for all combinations of existing flags and then updating the conditionals correctly with the new one you're trying to add. I know I have done this a lot in my career, which frankly has been very, very painful. I think this example is quite representative of the code you might find in most pieces of software written any time in the last several decades. And let's abandon all these issues, actually. Let's try to solve our problems using state machines. Before I proceed, I do want to have an accessible and practical definition here. So a state machine is a piece of software that accepts input and generates a deterministic output. If you think that that sounds like all software ever, you're not wrong. Almost every software is a state machine of one sort or another. Digital computers are primarily oriented to facilitate the creation of software state machines. And the hardware of the digital computers itself is an implementation of a particular state machine. The term state machine comes from the fact that distinct from the input and output, the software has settings, values, and data. And by the way, these are all names for the same thing, state. This is what we mean when we say state. The state may change what input is accepted and what output is produced for the next input. Let's look at our password reset problem as a state machine. So some important things to note here. We start with the initial state where we have the password. The transitions are represented in squares. The top part of that square is the input, and the bottom part has one or more outputs. So having a password and having a token in flight are two different states, which means that once you've generated a token, the old password is no longer valid. This ensures that if your account's been taken over or your password has been compromised, you can reclaim your account and shut out potential attacks as soon as you click that reset token button. So when we get the reset token input, we generate a token and switch to the token created state. And in this state, we can only wait for the new password entry as an input. And as soon as we get that, We save it and expire the token and transition back to the have password state. Here is the state machine implemented implicitly, because I promised that every program, every software ever is a state machine. The output generated for each input is determined procedurally, and that is why I call this an implicit state machine. No attempt is made to represent the inputs or outputs explicitly. In other words, though the solution is a state machine, any interesting properties of state machines are disregarded. As a result, potential benefits in the form of correctness, maintainability, and simplicity are lost. Let's look at the same example, but with a small refactor. This is only a minor variation from the first example, but it does have one interesting consequence. The determination about whether to generate one of the possible outputs, that is, generating a token or saving a password, is now based on an explicit single variable with all of its possible values enumerated. The benefits of representing this explicitly becomes more and more apparent as your requirements and solutions become more complex. What if you wanted to allow the same token to be sent multiple times to the same user? What if you wanted to add backup code? Making your conditional checks explicit makes it simpler and thus easier to test and reason about. You're less likely to run into unintentional bugs just because you forgot to update an if-else statement with a new variable or a new combination of variables. So, explicit state machines make the complexity of your system more maintainable, thanks to fewer control flow operations. You can always refactor your code into multiple explicit state machines that plug in together to represent a largely real system. This is essentially what I'm planning to do with my TLS implementation, where anything that feels mildly complex gets to have its own state machine. And then I just plug it into with the other state machines out there. When the system under test is implemented using an explicit state machine, certain useful assertions become easy to generate automatically. This has multiple benefits, including reducing the overall cost of developing and maintaining the test suite, as well as improving the overall quality of the test suite. For example, here, we know that there should be at least 4 test cases because we've explicitly listed out all possible inputs and states. And here's the secret. If you're using a good state machine library to define your state transitions, you only need to test the transitions you've already written, because invalid transitions are disallowed and will be rejected anyway. Visualizing an explicit state machine is easier, and we've also seen how useful it is, especially during the design phase of your project, where you're trying to find a sensible state machine implementation for your system. So, all right, let's assume that I've sold you on the benefits of state machines. You all like it as much as I do. And you want to incorporate them in your system. What do we do next? So that part can actually be quite daunting. How does the explicit state machine interact with your code? Because the whole project isn't going to be one big state machine, right? You'll likely want to build components as state machines, and then you'll likely have an interface that exposes the machine. So first, you'll need to identify what those components are that need to be implemented as state machines. And as a rule of thumb, when you see something like this, with or without typos, think explicit state machines. And now that you've built the machine, how exactly do you incorporate it in your system and expose it via an interface? Well, the users of your software don't and should not need to care that you implemented a state machine. As a user, all I know is that I forgot my password and I would like to click some buttons that would help me reset it. So if you go out there and look for state machine libraries on PyPI, you'll find a lot of options. All of these have their own ideas about what that interface that you expose should look like. I like Automat because it largely encourages me to design my library in a way that makes the state machine be a black box implementation that the users don't get to see. The API you expose to your users will plug into the state machine, And that interface has nothing to do with the state machine itself. And by that I mean that Automat is very careful to avoid exporting any public information about the fact that you're using it, like adding any extra attributes to your class and such things. If you have any object that has a reasonably well-defined exterior interface, where you can say, these are my methods that I care about implementing properly, Automat easily lets you turn them into state machines one at a time. Automat also has a very strong opinion about managing state. When you ask it a question like, how do I get the current state of a state machine? It clearly says, you can. So the interface that the rest of your code cares about is completely separate from the state machine implementation. This means integrating an explicit state machine is no harder than defining a new class. One major reason for having a state machine is that you want the callers of the state machine to just provide the appropriate input to the machine at the appropriate time and not have to check what the state of the machine is. So if you're tempted to write a bunch of if-else statements based on the state of your machine, Automat doesn't let you do this. Instead, it requires you to make your calling code just perform that action. And you would define the valid transitions like this. So you basically delegate the validity of that transition to your machine definition. Here, send message is the input. This is Automat's way of defining transitions, by the way. So the first argument is the input. Enter defines what the next state should be. And the last argument is a list of outputs that the transition should provide. This is also represented when we visualize this machine, and this ensures that there's only one valid transitions, which we can confirm via such diagrams. And we can explicitly test these transitions. We delegate the responsibility of making the other behaviors impossible to this internal explicit state machine. It's essentially an implementation detail you don't need to separately maintain or test as a blacklist. And this is part of the state machine as implemented using Automat. And don't worry, you don't have to read through this, follow this. I'll post links to these examples at the end. And also, by the way, the state diagrams that we looked at previously to design our state machine were also generated using Automat. So now that we have some practical guidelines to work with explicit state machines in the real world, let's look at the bird's eye view of our design process. If you're designing a system, threat modeling it as early as possible is ideal. If there is data at rest, for example, our token and the forgot password example, you have to be mindful of the scope and invariance of that data. These are formally referred to as assets, and identifying and protecting against possible threats to these assets is crucial. Threat modeling our assets isn't enough, though. We also must consider how those assets are used in our system. From our example, having identified the essential security properties of the token through this process, the system now has to guarantee those properties. And in order to provide those guarantees, we have to analyze the flow of state through the system. The more state there is, the harder it is to study the flow. Explicit state machines help us manage the complexity of mutable state by unifying it and laying out the relationships of different inputs and outputs and their corresponding valid states. So, well, when exactly should you use an explicit state machine? In an ideal world, always. But as a practical rule of thumb, they're especially useful when you're writing long and wide Boolean expressions that wrangle lots of variables in your conditional checks. And also, to wrap up, here are some references to help you with your state machine journey. The first one is a series of blog posts that walk you through understanding what a state machine looks like and how to make your software use it. The second link is a link to Automat. It is really good for helping you port your crappy legacy code to state machines. The last one is a combination of all the examples that we used in this talk. And thank you. We're going to have an open space about state machines at 5. Do come if you're free and around and interested. Thank you. Okay, are there any questions? Questions? Yeah, there is a question.
Could you please come back to the slide with the graph, please?
With the state diagram, you mean?
Yeah, the diagram.
Okay, give me a second. I don't.
Yeah. So does it mean that if I hit the reset password button, I have no password anymore, so I cannot log in anymore, or not?
Then you're, so yes, in that case, the token becomes the only thing that lets you access your account. So the idea here is that your password or your token is an entry point that lets you, the user, access an account. And at any given point, there should only be one entry point.
Okay, so isn't it like, maybe it's for the example, but it's like a denial of service, right? If I hit reset password for arbitrary users, I will all prevent them to access the service, right?
You can get locked out of your account, which is actually for your own good, because if your account has been compromised and you've lost a password, as soon as you realize that, the first thing you should do is invalidate any access that is not coming from you to that account.
Okay, all right.
Thank
Thanks.
You.
So melee machines or more machines? I'm joking. In an ideal world where instead of Automat you used a handcrafted DSL for describing FSMs, is there some specific killer feature that Automat doesn't have that you'd like to see?
I would delegate that question to Glyph, who's the author of Automat. And I can repeat that over Mike if he has it. Okay, you should talk to Glyph later at the open space. He'll think of an answer until then.
Cool, thank you.
Or maybe a new release of Automat is impending.
Hi. So I see usually state machines represented as graphics and then implemented in code. Do you have any utilities or any recommendations for transforming from one to the other? So drawing it out and then auto-generating.
So Automat has a visualize feature, a tool, where you don't even need to define actual actions. You can just define the name of the input as a method or whatever it is that you would prefer, and run a tool audit that generates graphs like these. And then you can do a sort of test-driven development on that and go back and fill things in as and how you think it should change. And it updates the diagrams also. So I really like that feature.
Thanks.
You're welcome. Any other questions? That's it. Okay. Thanks, everyone. Indicate a bug, because user A could change user B's password. The one-to-one mapping between token and users has a serious consequence. We should not choose our tokens from an easy-to-guess sequence. If we did, an attacker who got a single token would find other users' tokens and reset their passwords. What we just did here, it's a glimpse of a larger process called threat modeling. My colleagues Ying and David gave an awesome talk on this yesterday, and I highly, highly recommend it. So our first modeled threat is the lack of uniqueness in password reset tokens. And our first API change is to generate long, random security engineer at Docker. I'm also the author of a pure Python TLS implementation, and I previously worked on Twisted. I really, really like state machines. I like them so much that I wrote a TLS implementation because I was looking for an opportunity to use state machines in a complex environment. But taking you through an entire TLS implementation is a little too much for a PyCon talk, I think. So instead, we are going to talk about a common problem that web applications need to solve, along with some security implications. We'll then solve the problem using state machines, as promised in the title. So let's dig in. We've all interacted with web applications that ask us to set a username and password. Let's design a service that provides password reset tokens to users who've forgotten their passwords. It should work something like this. The user clicks a button, receives an email that contains a link, which itself contains a password reset token. Clicking the link sends the token back to the service and convinces it that the user should be allowed to type in a new password without entering their old one. Some things to note here. We see that a single token belongs to a single user. If multiple users had the same token, it would clearly.
Good afternoon. So I think we're going to go ahead and get started here. Our next speaker is from Docker, and her name is Ashwini. She's going to be talking about the design of secure APIs for state machines, and we'll get started.
Thank you, everyone. I hope there's no fire in between. So hoping that everything goes well. Today I'll be talking to you about designing secure APIs using state machines. My name is Ashwini. I am a tokens via cryptographically secure random number generator. What this means is that essentially we're taking an enormously long sequence and picking numbers randomly from it, with big gaps in between. It's true that if the largest token is very large indeed, nobody would be able to guess anybody else's token in a reasonable amount of time. Maybe then we don't have to worry anymore about our tokens. Maybe we're all done here. Maybe the problem is solved. But hold on, let's take a step back. This diagram also makes it clear that the token passes from one trusted party to another through intermediate